Hello everyone, this is our part 2 on groundwater. So the first thing we're going to start with is porosity. Porosity is simply the percentage of pores or empty space in the rock or sediment. So what you see here, for example, we have grains right here. Let me use another color right here. So we have grains right here. And between the grains, we have this empty space right here filled with water. That's what you call porosity. So porosity simply is the amount of empty space you have here with respect to the whole volume of the rock. And how do you calculate the porosity? Porosity is equal to the volume of pore space, this space we have here, the volume of this space, divided by the volume of the whole sample in centimeter cube, of course. So how can you find the porosity of the foreign materials? So to find the porosity, for example, of this materials, like we have gravel, we have sandstone, we have shale, and we have clay. So for example, to find porosity for gravel, let's write it down here. Let me choose another color. So porosity for this first material right here, gravel. Gravel basically are big particle. They look like this, big particles. And so porosity is equal to volume of the pores divided by volume total of the sample. So here we have the volume of the pores right here, 200. So we're going to plug this here, 200 centimeter cube. And I forget to do here multiply by 100, by the way, because it's a percentage. So you have to multiply 100 to get the percentage. Divided by 600 centimeter cube times 100, and that would be equal to 33.3 centimeter, cancel with centimeter, no units, and percentage. And that's the percentage of this first material, 33.3%. That's a loss of empty space there. So your turn. What is the porosity of sandstone, given that the volume of pore space is 150 and the volume of the sample is 610? So again, all you have to do is multiply 150 divided by 610, and that gives you, if you divide the numbers, you get, okay, you get here 24.6%. Again, always remember to multiply this by 100 here. Okay, 24.6%. And for the other one, for shale, you got 55 divided by 950. And this one give me 5.8%. Okay? So it's very simple. Divide the empty space divided by the volume of the sample. You get the number, you got the porosity. So the question number 2 asks you, which material hold more groundwater? Of course, the one that has more empty space is the one that will hold more water. So number 1 is gravel, second is sandstone, and the last one is shale. Okay. Calculate the porosity for the well-cemented sandstone and a poorly cemented sandstone. Explain your data. So This one is cemented, well cemented, meaning that this gray brown color here between the grains is cement. And this one here where the water is located is the empty space. So this one is well cemented because you have a lot of cement, and this is poorly cemented. You have a little cement right here. So let's look, what do you think in terms of porosity? Which one would have more porosity? The well cemented or the poorly cemented? So we'll see. So to find out, we'll find the porosity for well cemented. So again, what you have to do, you divide 50 divided by 1000. And so here we got 5%. And for the other one, you divide 213 divided by 852, and that would give you 25% of porosity, which makes sense because the cement closed the empty spaces here. But we have a little of empty space, you have more of empty space here. So well cemented has low porosity and poor cement has more porosity. And what makes the porosity decreasing is the cement between the grains. So here we have porosity and effective porosity of common earth material. So the thing is that when you have the porosity, it does not mean that all this porosity is useful. For example, look at the clay, for example. Clay has a porosity up to 55. But look at the one that is effective, only 1 to 10. Silt up to 50, but the effective one is up to 30 only. Sand has 25 to 50 total porosity. The effective one is up to 35, which is good. Gravel has up to 40 porosity total, but we have 20-35 effective porosity. 74 sandstone and so on and so on. Shell, as you see here, has very little effective porosity. Limestone has 115 and granite has less than 1. Less than 1 if granite is not fractured. But if the granite is fractured, it has cracks, this will increase, of course. We're going to see this paradox. Why, although the clay has high porosity, the effective porosity is only 1 to 10. We're going to talk about that later. But let's look at the different types of porosity. We have primary porosity and we have secondary porosity. Primary porosity are those who are formed during a rock formation and lithification. And this is typical for sandstone and, for example, limestone, for example. Those are porosity developed during the formation of the rock. This porosity or primary porosity depends on the size of the grain, sorting, and compaction. We're going to talk about this in the next slide. Secondary porosity, however, is the one that develops after the rock formation. For example, after the rock formed, this rock can be fractured, they can be faulted, they can be dissolved, and that contribute to increasing the porosity of the rock. Going back to the primary porosity, as I told you before, this porosity depends on how sorted are the sediments. So here the first one is well sorted, meaning simply that the grains are of the same size. When the grains are the same size, we say that the soil is well sorted. In this case, I can see here we have more porosity. How about poorly sorted sediments or soil? You can see, for example, you have different size. Poorly sorted means simply different size. Unlike sorted, when you have same size, poorly sorted means you have different sizes. You have big, we have medium, small, very small, and so on and so on. What happened is that here, this very small particle right here, they fill the space between the big ones, reducing the porosity. We have also cemented grains, as we talked about before. The cement between the grains reduces the porosity. Also, when the crystals are interlocked, like for example in igneous rock or metamorphic rocks, this also reduces the porosity. Clay-rich rocks, of course, they have high porosity, but you see later that although clay has large empty space, the effective porosity, the one that is useful, is very little. Another factor is also compaction. If you have, for example, grains like this, as opposed to if you have compressed particle, if they're compressed, the porosity will be reduced. So when the soil is compacted, the porosity is reduced. But when the soil is loose, the porosity is higher. So that's what causes the porosity being higher or lower, especially primary porosity. Secondary porosity, as we say, this develop after the formation of the rock. This include, for example, fracture. You can see here loss of fracture right here, right here, right here, right here, right here, for example. This fracture contribute to making more space in the sand. Okay? You might have also dissolution. For example, limestone dissolve. When dissolved, it leaves this empty space, and those empty space, they serve as pores. We have also fractures, for example, in shale. You might have little fractures in here. Those fractures also contribute in making more empty space. Fractures in granite, for example, that's another one. Or fracture in limestone. So all those happen after the formation of the rock, and they increase the porosity of the material. And when I say increase the porosity, it also means more water inside the rock. Now we get to another important term, which is permeability. And we're going to look at the definition later. So again, looking at this example we have here, the question asks you, which rock has more porosity, well-cemented sandstone or poorly cemented sandstone? We did this before, and we found that the first one has 5%. Okay, this is 5%. And the other one, the poorly sorted materials, when you divide 213 by 852, that would be 25%. Okay, we know that. We did this before. So we know that the well-cemented one is less had. Okay, we know that. We did this before. So we know that the well-cemented one is has less porosity than this one. Now the question for you now, which rock allows the groundwater to flow through? This one right here, the well-cemented one, or the poorly cemented one? Of course, as you see here, that the poorly cemented sand is allowing the water to go through. It goes from one pore to the next pore to the next pore, and so on. So the water flows easily. And the ability for the water to flow through is called permeability. So we say in this case that this material right here is permeable, and this one right here is less permeable. And that's the definition right here. Permeability is the ability of a material to allow fluid to pass through an interconnected network of pores. When I say fluid, this applies not only to water, but also to petroleum or oil. So this permeability depends on factors such as the number of available conduit. For example, we have 1 here, we have 2, we have 3, we have so many conduit. So this also is important, because if you have no conduit, then permeability is less. The size of the conduit. Of course, you have big conduit, we have more probability. If you have small conduit, is very little probability. Straightness of conduit. Like if, for example, you have a conduit like this, if it moves like this in a curved path, it does not really cause the water to flow easily. But if you have something straight like this, it's much better because the water goes faster and slow and smoother from one port to another. Unlike if you go like in a curved path like this. So those are all the factors that affect permeability. So here we have permeable materials, which allows the water to flow through. And impermeable material are the one that does not allow the water to go through. So these are examples here of rock type, their porosities, and their permeability. Sandstone, for example, has 10 to 30 porosity, which means it has a loss of storage. Remember, porosity gives you an idea about how much water the rock can hold. For example, sandstone can hold up to 30% of the water, but this one holds, basalt, for example, hold only up to 5%. Permeability, however, gives you an idea about how much the water is flowing. For example, here we have 10 to 1,000 millidarcy. Millidarcy is the unit given to permeability. Darcy is a scientist who study groundwater a lot, and he come up with so many equations, including the equation we're going to talk about in a few minutes. So what is the relationship between sediment type and permeability? So if you look here, for example, we have sediment, clay. It has very low permeability. It's impermeable. Silt has low permeability. Sand has moderate to high permeability. Gravel, high permeability. The relationship, simple, is that when as the size of the particle increase, the permeability also increases. Okay, very simple. What is the relationship between the sediment type and potential yield of water well? What we mean by this is that how much water you can pump. Let's say you're pumping, for example, from this. Let me get here. If you have a well, for example, that reach these rocks, for example, how much water are you gonna pump per minute, as opposed to this well, for example? Of course, here you're gonna pump more water per minute than here because the water here go flow easily. So you might have a loss of water, a loss of gallon per minute of water. Let's say, for example, you might have, let's say, for example, here, 200 gallon per minute. And here you might have probably 10 gallon per minute. Why? Because this material right here is permeable. The water go fast, go through easily. But this one go very slow, so you get only a little amount of water per minute. So that's what you have here. We have this one here is clay. This is clay. This is silt. This is sand. And this is gravel. So because here gravel has high permeability, it's like this one right here, the water can go, let me choose another color here, let me choose blue. The water can go easily and move through the well. So in this case, because gravel has high permeability, the amount of water you can pump per minute is from 500 to 3,000 plus gallon per minute, which is a lot. Unlike the clay, for example, you would get only 0 sometimes to only 1 gallon per minute, which is not, which is almost nothing, which is nothing actually. So farmers, for example, are looking for this type of soil or rocks here beneath their their well, for example. Because if you have gravel, you'll be able to pump more water. If you have clay, for example, you're going to pump less. Although there's no well that is going through clay and stopping clay, because this is definitely nobody drill a well up to clay. But this is just to show you that if you drill a well to clay, you get almost no water. Sandstone is fine because sandstone still you'll be able to get from 10 to 100 gallons per minute. So again, the relationship between the sediment type and potential yield of water well, how much water you're going to pump per minute or gallon per minute, as the size increases, the amount of water that you get, how many gallons per minute you get increase also. The typical well yield also increase. Okay. So the larger sediment size, the higher the permeability. And that's what you have here. When the larger particle, when you go from clay to gravel, the larger the particle, the higher permeability. And the larger sediment size, the higher the potential yield of water well. Okay. Going back now to the effective porosity I talked about earlier. If you remember, I said that the porosity of clay is high, but its permeability is very low. So how is that possible to have high porosity and low permeability? And that's typical to clay. If you go back to the previous slide, you see that porosity of clay reaches 55%. But the permeability is very low. So how come you have high porosity but low permeability? So the reason is, there are a couple of reasons. Clay happen to be in tiny flat particle. Like for example, this is the clay particle right here. Let me use another color. This is clay particle, and that's another clay particle. And this is the empty space between them. Okay? So what happened, if this represents, let's say, for example, 55% total porosity, 48% is trapped by the clay particle because of electrostatic forces. So as the water moves, 48% is trapped in clay. The clay holds it. Okay? How much remains then? It's only, if I say, for example, if I have 55 porosity and 48% is retained because of clay, then we have only 7% left. This 7% here in the middle, the white part here, is the one where the water can flow. So the water flow in only 7% of the volume of the porosity. The remaining stay attached to the clay. So although we have a high amount of porosity, but most of it is attached to the clay. The clay holds the water tightly. So you can see the porosity is high, but effective porosity is from 1 to 10. In our example, we have only 7%. So how can I get those numbers? We need to use an equation. Total porosity equals effective porosity plus retention porosity. For example, here, let me clear this out. So here, for example, this is the total porosity. Total porosity. Total porosity, we label it as NT. NT would be total porosity. We have 55%, right? And retention porosity is this one right here. Let me use another color to indicate that one. This represents NR. And the effective porosity is the one, the white part right here. That's effective porosity. So total porosity, this is equal to retention porosity plus effective porosity, which is clear here. So if I would like to plug the numbers here, total porosity is 55 equal effective porosity, which is 7%, remember? 7%, plus retention porosity, the one that is held by the clay particle, is 48%. Plus retention porosity, the one that is held by the clay particle, is 48%. So NT equals effective porosity plus retention porosity. And retention porosity, again, is the water trapped and is not easily drained through the pores. Let's look at example. So we have here an example. Let's look at this example. Determine the effective porosity of the following samples. This is the material. We have clay, sand, gravel. The total porosity of clay is 50%. The total porosity of sand is 35%. The total porosity of gravel is 30%. Look at the clay. Clay has the highest porosity. Retention porosity for clay is 45%. A loss of porosity is retained by clay particle. For sand, we have only 5% retained. For gravel, you have 2% retained. The question asking you, find the effective porosity, the one that is useful, the one that go through from pore to pore. So I'm doing clay for you here. So you write the equation. N total, porosity total, equals effective porosity plus retention porosity. Then to find Ne, you put Ne equals Nt minus Nr. Effective equals total minus retention. And once you get this equation, it becomes easy. So all I have to do now is plug the numbers. Effective porosity is equal total porosity. Now for clay, total porosity is 50%. So I'm going to put right here. Minus retention porosity is 45, right here. And 50 minus 45 is 5%, right here. Okay? So your turn now. Given this equation, given sand is 35% and retention 5%, what is the effective porosity? So what you should do, same thing again. All you have to do is follow this equation. We have Ne, which is what we're looking for, equals total porosity, 35%, minus retention porosity, which is 5. 35 minus 5 would be 30%. And that's 30% right here. Now for the gravel, again, you can pause the video, again, you can do it yourself. It's easy. We have everything here you need. So total equals effective plus retention, and equals total minus retention, and equals, you plug the numbers here. My numbers are total for gravel is 30%, and retention is 2%. 30 minus 2 is 28%. Okay? So what you see here, this is 20% right here. Let me write 28%. So you can see here, although clay has a high porosity, huge amount of empty space, 50%, but the only effective porosity is 5%. That's why it has very low permeability. The water only go through this 5% only. And that's why clay is impermeable, 10 to negative 11 meter per second. And look at the gravel. Gravel, although it has only 30% porous total, the retention is only 2%, means the amount of water that is held by gravel is only 2%. But the effective porosity, the porosity that allow the water to go through, is 28%. And that's why the probability for gravel is high. And again, that's, I show you the work, and it's pretty clear that you can see now why clay, although it has high porosity, its effective porosity is very little, and that's why it has very low permeability. And now we can write this relationship between the two. The smaller the particle size in like clay, for example, the lower the permeability. The larger particle, like in gravel, has high permeability, and small particle like clay has low permeability. And that would be end of part 2. Thank you.